Welcome.
Thank you.
Now, for those of you familiar with In Conversation With, you know that we normally start at the beginning of a guest's life. But this time, we're going to start with last week. Recently, 100 young scientists from around the country, including 3 from LBNL, received the prestigious Presidential Early Career for Scientists and Engineers Award. Jeff Neaton was one of the scientists chosen by President Obama to get this award. Statement announcing the Obama said, extraordinarily gifted young scientists and engineers country. With their talent, creativity, and dedication, I am confident they will lead their fields in new breakthroughs and discoveries and help us use science and technology to lift our nation and our world. No pressure.
Right.
Awardees were selected on the basis of 2 criteria: pursuit of innovative research in the frontiers of science and technology, and a commitment to community service as demonstrated through scientific leadership, public education, or community outreach. Now, Jeff, what were you recognized for as far as research? What did the president see in your work?
That's a very good question. I didn't get a chance to talk to the president about my work. I think that this kind of award, as I understand it, is for a body of work and not for one particular thing. I think it's meant to recognize in this case some success that I've had with many collaborators that I've been fortunate to work with. Understanding the nature of current flow through small nanostructures in the past few years.
And how did you find out about this award? Did your agent call you at 5 in the morning?
Well, yeah. Normally my agent calls later in the morning, but no. Actually, so I found out about it in kind of a strange way. I got an email from somebody whose name I forget. In the body of the email, it was a message from John Holdren, who's the scientific advisor to the president, the email was sort of addressed to not to necessarily me, but generically addressed as an awardee, it actually there was a couple of typos in it actually, and so it was actually coming from the subject line of the email address. The person that it was coming from was different from the person. It wasn't from Holdren, but it was signed by Holdren. So I had to say I was kind of excited about it, but then I was also my inner scientist was a little skeptical about that, its veracity. But then so the next day there was so for 24 hours I kind of kept it to myself. But then the next day there was another email that said the next day there'd be a press release, a White House press release, and that's when I felt like it was for real. So.
And you found out about this back in August, is that right?
In July.
In July. And then when did you actually go to the White House?
Last week.
Last week.
Yeah.
Now, I've had a lot of questions about this ever since people found out that you were going to be here today. They want to know everything about the White House visit. So I'm just wondering if you can walk us through the day that you received the award. What did you have for breakfast?
I had a cup of coffee I didn't eat well that day, I think. So it was a long day, and my wife, Em, and my parents were able to be there. So actually my dad happened to be in D.C. and he heard about this, and so my mother said, well, I'm coming, and so you could have a certain number of guests, and so it just so happened it was great that they could be there. But the day started with a tour of the White House at 7:30.
Wow.
And so,
actually, I'm going to drink some coffee while you're telling this story.
Yeah,
I'm getting sleepy.
Exactly. Fortunately, I was jet lagged out of my mind for other reasons, so it didn't matter that much. But basically, we had kind of the conventional tourist tour of the White House, and I'd never been to the White House, so it's one of those. I've been to a lot of things in Washington and seen the the monuments and things, but I've never been to the White House, and that was
And
pretty
you're not a
exciting.
reality star, so you may not have gotten in otherwise.
Right, there were no cameras following me at that point, so I think it was okay. But there was a fair amount of security, and I remember they checked our driver's license twice and against a list, and you were on this list, and there was 100 of us lined waiting in a long line outside the gate. It was very cold, so we kind of toured it, and we had this kind of conventional tour, and all the rooms were roped off, and it was later that day it was nice because then we returned to the White House, but the ropes were taken away, and we were actually at an event at the White House, and it was kind of exciting to do that. But yeah, so there was a White House tour, and then there was a Department of Energy ceremony and a Department of Commerce ceremony, and then a White House thing, and it basically went the whole day. Yeah.
And you did have a meeting with Steve Chu. You were in the room and had a little conversation with Steve Chu.
I did.
What did he say to you?
He asked me how things were doing at Berkeley Lab. Actually, he mentioned, so his office was had sort of a panoramic view of Washington. And so we got to go into Steve Chu. He gave us about 10 minutes, and there were 12 DOE awardees. There's 100 awardees, in total, sponsored by all sorts of different agencies. But there are 10 or so awardees sponsored by the Department of Energy. So the 10 of us went up to Steve Chu's office, and he has this panoramic view of DC. And so somebody says, "Wow, nice view," and he said, "Not as good as Berkeley." And so then, of course, when I went up there to receive, they took a photo of us receiving the award with him, and I told him, I said something like, "Well, it's not as good as Berkeley, and it's certainly not as good as your house, because I've been in your house." And I think he probably thought that was a little creepy, but
well done, Jeff Neaton. Well done.
As it turns out, that we had the same real estate agent, and while my wife and I were looking for a house, she was like, our real estate agent, Maya Trilling, really tremendous real estate agent. Anyway, she basically was like, "You got to see Steve Chu's house. It's Super Bowl Sunday last year. No one will be there, but we're showing it, and it's just an amazing place. We think it's a little out of your range, but you got to see it." And so yeah, there's a kind of a 3-bridge unobstructed view from his living room of the entire bay, and so we're kind of in this house, and this is probably one of the things I remember about. I won't go into a bunch of house hunting stories, but when you go through these open houses, they're all staged, and so you kind of see things you normally expect to see in a staged house. But in one of the rooms in this house, of course, was something distinctly his office. And it had all of the same physics books that I had, except that there was a Nobel Prize on the wall. So that was nice. Something I'd never seen in a staged house before. So I assumed that was, I happened to know that was real. But yeah, anyway.
So after the White House tour with your family, and then the DOE trip, you did go back to the White House for the official function, the ceremony. And what happened there? You go back to the White House. First of all, did you walk through the front door of the White House? Did they let you through the front? What did that feel like? What was going through your mind?
Yeah, no, I didn't walk through the front door. You actually, I think you walk through I want to say the west side of it. The east side of it. I feel like so what happened is that there's kind of a long line, and there's sort of Secret Service agent, looking at your ID. And then you walk, then that sort of enters you into this complex that includes the Department of Treasury, and then you walk in front of the Department of Treasury up to another Secret Service agent with another list and checking your ID again. So just in case in that 100 feet, a reality TV person got in there or something. And then you walk through a small, metal detector room, and then you kind of walk into the east side. And yeah, we kind of gathered in the east wing and the east room, where there are big pictures of George and Martha, up on the walls, and basically there were these risers, and there was 100 of us, so we got on the risers. And
so, was there any food?
No.
It wasn't a gala dinner?
No food.
Did you mention maybe to the president? Did you say anything like, "How am I supposed to lift up the nation and the world on an empty stomach"?
I never said that to him, but yeah, perhaps I should have, yeah.
So you get in the room and you get on risers and wait for the president?
Yeah, then after some organization by his staff, they were sort of on their BlackBerries. He's coming in 90 seconds. He's coming in 60 seconds. Blah blah blah. And then they just like on in the press conferences on TV, he walks down this long hall, and I would call it more of a saunter. But then and then you could see him coming, and then he kind of comes in, and as he comes in, everybody spontaneously broke into applause. It was kind of a very exciting, a moment. I thought, it's a little, when I heard about this, I was sort of thinking, well, we're going to take this picture of the president, he's going to step into it and step out of it, so what, at some level. And he might not even be there, there's got to be more important things to do. But I think when he showed up and he more or less did step in and step out, but he gave us 5 minutes of his time. But it was a lot more exciting, and there was this sort of rush of emotion and patriotism that I did not expect to feel, and it was just really kind of just to actually be in the room with the president is actually something that was more special than I thought it would be, and it was actually. And here's the picture, and where is Jeff Neaton in this picture? Where's our star? There he is. Pretty good, actually. There is Jeff Neaton. I'm not sure I would have been able to find myself in there. So what's the one thing that you think you're going to remember most about this experience? I was happy to be able to shake his hand. So actually, when at some point he was talking to us and he sort of said, "I got to go," and at that point it was like a rock concert. I mean, the guy was immediately surrounded, and I was just close enough to get a chance to shake his hand. And I think people in the immediate vicinity did before he was pulled away. So that was kind of nice. Wow. Now we did something this time that we've never done before on In Conversation With, which is to solicit questions from the audience. So we have just a couple questions here. First one is from Deirdre in '67. When I watched the show West Wing, the White House, or at least the replica of the White House, looked a little run down. Do you think the White House could use some sprucing up? I think it has a lot. It's very charming. The White House is true. I would. Is it homey? Would you call it homey? Well, I think you could. I'm not sure the part of the White House that we saw was all that homey. It was a little bit more formal, but it looked in pretty decent shape to me. Okay. Yeah. So you're not going to show up with a paintbrush anytime. Not going to show. Yeah. At Tracy in Building 66. Would like to know, is Obama in person as he is on TV? Obama is cute, yeah. I think so, yeah. And then David, he had a lot of questions, David from 67. But here's one. What kind of handshake did you get from Obama versus Steve Chu? Firm, limp, etc. I'm not sure what kind of a bowler Chu is, but Obama's record there is not impressive. And I guess that says something about the strength of his wrists. So can you compare and contrast maybe the handshakes you received from these two? Yeah, I never thought about that until now. I think that Obama's handshake is a little bit cooler, and maybe Steve's a little firmer. There you go. You heard it here first. Okay, so a little less than a week ago. I think others could probably chime in on that too, but anyway, yeah. So a little less than a week ago, you were at a little more than a week ago, you're at the White House, receiving an award for your work as a scientist. Let's find out how you got there. Where were you born? Minneapolis, Minnesota. And is your family still there? Yes. What did your parents do? Be watching this. So my father's a professor of biostatistics at the University of Minnesota, and my mother is a homemaker and raised us fearlessly. And how many siblings do you have? I have two siblings. I have a brother and a sister. Where did you go to high school? Well, in Minneapolis, it's pronounced De La Salle High School. It's in so if you're, apologies to the French, and it actually was on an island in the middle of the Mississippi in downtown Minneapolis.
Go Islanders.
That's right, we were the Islanders.
Yeah. At one time you said about high school that you didn't really pursue intellectual activities in your early high school career. What did you like to do?
Oh, yeah, I certainly did not. I probably didn't start taking school seriously until the end of my high school career, but I was actually, and this may be hard to believe, I was a jock, so I really liked to play sports, and I played baseball and soccer and basketball and things, and so not particularly well, but I lettered a few years in those sports, and I think I spent most of my time in extracurricular doing that. Yeah.
Well, tell us about Dennis Wadley.
So that was sort of in the later part of. So he was my English lit teacher in high school, and he was really memorable because I think he definitely taught the toughest class I took in high school, and actually probably in the first couple of years of college as well. Really, so he, I think for me, he's memorable because he really taught me how to write in a way that, and made me focus, I think, on school. He kind of got my attention.
And also got you to think critically and analytically as well.
Yeah, he did. I think somehow, so in this class, he basically introduced us to a whole range of literature, and I was did as an undergrad a science degree, and you do that in the U.S. You actually do have to take electives, and I had to take literature classes in college, but nothing ever compared. Nothing was ever even close to the 2 years that I had in high school with Dennis Wadley, and I think he really. He actually, basically we would have these in-class essays, and he would teach us how to write an essay both in 45 minutes and a longer format. And he was extremely hard. He was basically, I think he is one that instilled in me, I think, qualities that I see as being of absolute importance to any scientist, which would be, creativity, but balanced with rigor and clarity. I think. Writing those essays in his class and getting all those C minuses and gradually, really got my attention. And I think he also introduced me to this, range of literature that I'm still, the list of books by my bedside and of books to read is just infinitely long. I think in part because of him. Yeah. So.
Now, toward the end of high school, you started taking academics more seriously. And you realized that you really enjoyed math and science.
Yeah.
What was it that drew you to math and science?
Well, I always enjoyed math and science, actually, and I think it always came rather a little bit easier for me, I think, than other things. I think part of the reason for that is my dad is a statistics professor, and actually, one of the things that from the earliest time. So I think there's kind of the origin of my scientific interest really comes from maybe a couple of things, maybe more than that, but one is that I grew up near an airport. So I grew up a mile away from a runway, the end of a runway, Minneapolis-St. Paul International Airport. So throughout my childhood, there are these giant planes flying overhead, landing and taking off. And so I had this, as a kid, interest in aviation, and it was about the time, of the space shuttle, the dawn of the space shuttle age. So that really caught my attention. And then my dad was a statistician, and he kind of had this, at some point he had a kind of a side consulting business that he started with some other professors. And as a byproduct of that, we got a VAX mainframe computer in our basement. And so this is when I was 10 years old, and so how cool is that? I mean, you've got this giant computer. Now, basically the hard disk was the size of a microwave, and it had 5 megabytes of disk space. But, the tapes, the whole, it was like a, early 70s sci-fi thing, and it was happening in my basement. So, the natural thing was sort of, what do I do with this? How do I, Dad, how do we, rule the world with this thing, or whatever you want to do. And so I actually, when I was, that's how I got my start in computer programming. I learned the basic language and on a VMS operating system that main. Because basically, it turned out that, well, at the end of the day, there was a terminal with a cursor prompt, and that was about it. So it was definitely not a PlayStation 3. But there was kind of that downer moment. But then I got to learn a little bit about programming, and together with my dad, I remember this vividly. Kind of taught me how to write this program that would test my knowledge of the capitals of the 50 states. Because I was in 5th grade, and so I had to memorize all the capitals of the 50 states. And so he wrote this program, and he kind of let me help him, and I learned a little bit how to use this computer that would just kind of pop up and say, "What's the capital of Montana?" And I had to type it in, and I'd have to get it, the spelling right and all that kind of stuff. And so anyway, so I think those two things, kind of already started. And both of my parents were very active in, took an active interest in helping me in my homework and things in those early days, and I think I just picked it up. So.
But your dad also influenced you in other ways as well. Even though he was a statistician, he wasn't abstract about it. He was very practical.
That's right. So,
and he instilled in you this idea that practical is good.
That's right. So he, he basically runs these big clinical trials that test different drugs that, the efficacy of different drugs for treating diseases like AIDS or HIV and AIDS and various forms of heart disease.
Mm-hmm. And you took that seriously. You wanted to do something.
He
practical.
set the bar high in that regard. I mean, I think in the end, I think you have he kind of sort of inspired me to think about applications that a little bit
So you graduate high school. Where do you go to do your undergraduate?
The University of Minnesota. And
what did you think you wanted to study there?
I was I think an engineering, some sort of engineering.
Because it's practical. Was that?
Because it was practical, and I think the airplanes and the aerospace sort of there was a vague notion of that, and it had a good engineering program, and I think a very good engineering program, and so I that's what I thought I would do.
So everyone in your program had to take freshman chemistry.
That's right.
Tell us about your freshman chemistry experience.
It was a disaster. Yeah. It wasn't unmitigated, but the lab part was awful, and in these, I don't know how it works these days, but we were graded on the percent yield, and I couldn't, I got very good with my ovals, with percent yield, and so it was really tough for me, and I do remember a moment where I had like a crucible and a Bunsen burner, and in the panic of this lab, I grabbed it with my bare hands, and I remember just holding it. It had been under the burner for a while, and I was just holding it. And then sort of started to realize that this is incredibly hot, and it is burning my, and so my hands are blistering immediately, and and then I remember throwing it against the wall because that was the first thing I could think of doing, and so my whole experiment was on the floor, and the TA was just head in his hands. So it was.
You took a souvenir from that class, didn't you?
I did. I at the end of it, I thought I needed to. I felt that I was owed something from the glassware shelf in that lab. That's right. I have a 500 milliliter volumetric flask at home from that experience.
Where do you keep it in your home?
It's in a prominent place. Yeah.
So the undergraduate curriculum was very structured at the University of Minnesota. In the third quarter, you took this Introduction to Physics class, which eventually got into some fairly high-level quantum physics. The problem was your instructor wasn't a great communicator.
That's right. He was a really very bright person, but it was tough.
And you got lost. And then,
totally lost.
Totally. This is what I find remarkable about your story, though, is that you take this freshman chemistry class and you didn't have a great experience. You're taking this intro to physics class, you're not having a great experience. For somebody like me, and maybe this is just a character flaw in me, I probably would have thought, well, I'm just not good at science. I'm going to go next door to the history department and see what's going on.
Yeah.
But not you. There was something in these classes that made you want to stay. What was it about this physics class, that, even though it was terrible, that made you want to continue?
Well, I think that in the case of the physics class, it was really just pitched at an extremely high level, and so it just introduced. So it introduced all of these concepts that were just not completely explained, and so it was a little bit hard to, internalize them for exams and such. But it just introduced me to these things that I had just no idea about, and I think it inspired me to learn more.
So there was something in there, though, that captured your imagination.
Yeah,
that made you say, I want to know more.
Some combination of math involved, which I was sort of always interested in, and and the fact that this was a challenge, and I was clearly in deep water, but I took it as a challenge. I wanted to I felt like I should be able to do this, and so I got it. Yeah.
Well, it's a good thing you did, because the following year you took a special relativity course with a man called Jimmy Kay. Tell us about Jimmy Kay.
So it was a quantum mechanics course. So that was actually a crucial point. So at some point I decided, so even after this physics experience, I was like, well, I'm going to major in physics then. I decided. So I actually changed my major from engineering, and because I was just like, this is kind of a little bit inscrutable, but I think I need to know more about this, and this just seems like college should, what it should be about is learning, about something you don't know. And I'm made aware of all these things I didn't know. And so it was I decided that I just continue with the physics curriculum. And then I took a class in sort of sophomore level quantum mechanics. And I think, so I had a professor, James Kakalius, who is affectionately referred to as Jimmy Kay by no one but a few people. I think a good friend of mine coined that, so he himself does not know that he has been, he's known as that way. But he really was one of these kind of amazing, game-changing kind of teachers. Very dynamic guy who, very much inspired me, and really, kind of was very clear. It was a tough class, but he was. But he just, was so exciting to watch that I thought, this is something I would want to do. I want to be like this guy. And, I remember when he came in, this is a quantum mechanics course, and he sort of said something like, in this class we're going to calculate the wave function of a baseball. And I just thought, okay, I used to like baseball, and it was just one of those things where, that was the way he kind of went through. And he was, I got to know him personally also. He was very accessible, and, through his office hours, and he became a mentor of mine, actually, at the University of Minnesota. And although that was my last class with him, he was sort of influential in my development, I think,
And he got you a summer job at 3M.
That's right. Yeah.
What did you learn? What life lesson did you learn?
I'm not an experimentalist, and I'm not an industrial scientist. I think that's what I learned. So I did. As an undergrad, I got to clean glassware in a lab in 3M, and actually I ended up doing my. So 3M, is a big deal in Minnesota anyway. They have a giant campus. That's half the size of the University of Minnesota probably. Somewhat east of the city. So I kind of, after class I would go over there and work in a lab there. And at the time we were working on, the group that I was in was working on some medical imaging applications of selenium photoconductors. And I was taking data for them and, analyzing it a little bit, and that some of that stuff went into my senior thesis. But during the time that I was there, I witnessed the management deciding to shut this group down, and so I saw firsthand, these very accomplished scientists lose jobs essentially, and they were kind of matrixed into another part of the 3M, but they were kind of forced by management because the project wasn't working out in management size, to do other things, and I was sort of, kind of now then alerted to that possibility and how real it is in industry, and it just seemed like a riskier proposition,
So Jimmy Kay wrote a popular science book called The Physics of Superheroes.
That's right.
Have you read this book?
I have not.
Don't you think maybe you should?
I should. I agree. So the funny thing about him is that, so he even gave a talk at the NAPS meeting a few years ago, but he has really, this part of him I was completely unaware of, but completely makes sense at the time.
He also has an Emmy. Yeah, for some internet stuff.
Yeah, he's an Emmy. That's right. That's right. That's right.
And I wish, I was hoping I could get a bunch of copies of the book and I could say, everybody look under your seat. But unfortunately, we don't have the budget for that. Sorry. So you ended up getting your Bachelor of Science degrees in physics from the University of Minnesota.
Yeah.
You applied to and were accepted at several graduate schools, but you chose Cornell.
I was also not accepted at several graduate schools.
Okay. Now, why did you choose Cornell?
I think because, again, I had this idea that, I vaguely wanted to do theory, and I wanted to do condensed matter physics, but I wasn't exactly sure what I wanted to do. I think it has been, I've never been one of these people that was 100% convicted that this is exactly what I want to do the whole time. And so it has a big department, and it's a very good department, and there are lots of people. And I thought I'm going to find something here,
You once said that your first year at Cornell was difficult and stressful, but then the first summer you got a job in somebody's lab. Whose lab did you join that first summer? Yeah,
I started working with Neil Ashcroft that summer, and he was actually he taught statistical physics that spring, and I remember that, and so during the course of that time, he's a very gifted teacher, and I realized this is a guy that would be very good to work with. I'm sure I'd learn a ton. And he's teaching this class, and the way it works at Cornell is you can work with somebody over the summer, and there's really no strings attached, and so on either end. And by the end of your second year, you better have something going for your PhD, but it doesn't have to be until then, really. So your first summer is kind of a get to know you, get acquainted with the people's research, and maybe it won't work out. And his class actually was. Pretty tough class, but I felt like I understood, and I was very motivated to do well. But I do remember that at the end of the class he had this exam, and it was basically a 24-hour exam. So you pick it up at 8 a.m. and you drop it off at 8 a.m. the next day. And basically there was something like 15 questions or something, and you have to do 4 of them. The other ones are extra credit. And so what that kind of means, is that sure you can do 4. But, if everybody else in the class is doing all 15 or trying to do all 15, then they're going to throw the curve, if there is such a curve. And so it's kind of a mental. And so basically I decided I'm just doing 4. And so I just did 4, and then I turned it in. I don't remember. That took me a while, actually. So for me, that was a lot. And I remember just turning it in and thinking, that's all it asked me to do. And as long as those are as good as I can make them, then that should be enough. And fortunately, it turned out okay, and I got a grade that was acceptable to join his group, and it worked out fine. And so, but I think I remember being very nervous about that because I thought that would be very important. But I couldn't. But I also thought, I got to draw the line somewhere. I'm just not going to spend. If he's actually asking me to spend 24 straight hours, working through these crazy problems, then maybe he's not the right fit for me. And it just turned out that
he was.
He was, yeah.
But so you joined his group, and he basically gave you the theory of what it meant to be in his group, and then he disappeared for the summer.
That's right. So he kind of met me once, and he said, I'm going to be gone until September. And so yeah, it was, as it turned out, and I traded some email with him, but what ended up happening is that, which was very useful, but I got to know the theory group there and all the students in this group, and I kind of realized after that summer that that's really what I wanted to do.
But at the end of summer came the end of your summer work with his group, and you went through a semester, and again you weren't quite sure what shape your graduate career was going to take.
Definitely not, because at the end of the summer, then there was no money for me to continue. So right. I was back to teaching, taking class, and so.
But then you got a phone call.
But then he, out of the blue, he called me into his office, and my impression would be that maybe he had been thinking to do this, but just hadn't got around to it. But meanwhile, I'm just thinking, well, this guy doesn't, it didn't work out, and I should look for something else. But yeah, so then he kind of proposed a project, and it sounded good to me, and I started to work on it.
And this was a very important project when he encouraged you to compress lithium. Right?
Yeah.
So tell us about that and the impact it has actually had on science.
Yeah, I think
of science.
So there's one slight parenthetical statement I would make, is that the project I signed up for was nothing like the project I did. So in fact, it was so orthogonal it's hard to believe it. So I signed up to work in a MERSEC. It's sort of these sort of NSF materials research science and engineering centers. And my project was to work collaboratively with experimentalists in material science and chemistry and help them do simulation. So this is my first. So my PhD project, as a 23 years old, I'm walking in and I have to collaborate with chemists, material scientists, and people outside my discipline, and do these simulations which I barely know how to do, in support of their experiment. And so you can imagine it was a really interesting. I think that was a very important experience for me to have. That has probably affected the way I view science. But it was impossible basically, and it took me the entire time I was there to do anything meaningful with them 3 years or so. However, it was very interesting because as soon as we started working with this group, Neil started saying, well, you should really have this side project, and so Neil is always interested in high pressure phases of matter, and he's basically famous for making a prediction that hydrogen, in its sort of elemental form, will become a superconductor if you compress it. So basically, hydrogen's a gas, right? And as you compress it, to very, at very high pressures sort of beyond that of the core of the Earth, it will eventually become a metal. First a solid, then a metal. So it will conduct electricity, and then at some point potentially superconduct. And Neil is famous for predicting this, that it would superconduct at room temperature under these pressures. So this is something people have been looking for 40 years, basically, since he predicted it. And so he's interested in compressing. So basically, he's interested in understanding how the periodic table is altered under pressure. And so one of the things he said to me is, well, looking at the first column of the periodic table, why don't you look at lithium? Because that also, it's isoelectronic in some ways with hydrogen, and it might be, you might find something interesting there. And I think it was more than that. I think he had some real suspicions about what might happen. But it was also meant for me as an exercise. I think he wanted to see whether I could do certain kind of calculation right. And so he kind of started me by saying, why don't you generate the band structure, basically, which is it's a calculation that's kind of standard for a young person like me. Why don't you generate the band structure for lithium and then do it for lithium under 8-fold compression and bring it into my office, and we'll talk about it. And so when I did that the first time, he said, okay, this looks good for at regular, for its equilibrium volume, but at high pressure, that's totally wrong. that can't happen, and basically there's a mistake there, and so he gave me a couple of suggestions, and 2 of them were correct. I had made mistakes, but it didn't actually change the qualitative result. And so then that started sort of, I would say, a year and a half of calculation, intense discussion, and out of it, came, I think, which is probably the most important result of my thesis, which is that as you compress lithium, it goes from a very reasonably good free electron metal conductor, and actually becomes an insulator, effectively. It becomes more and more insulating, which is something that up until that point was, or at that point was viewed as very counterintuitive in high pressure physics. Usually as you compress things, they become more conducting. Mm-hmm. And so...
and this was completely new. This wasn't something that was in the textbooks anywhere. You were doing novel research.
Definitely, and so that this was not an expected result. I remember that he actually, at some point, I think he trusted me, but he actually had somebody else, do a calculation, an independent calculation, to check one of my structures, because it was just some of those things where it was hard to, at first, and I later found out about this, but it was at first really something very counterintuitive, something you would not have expected to happen. And later, we rationalized it. The way we rationalized it, I think it makes perfect sense, in retrospect. It initiated a lot of work in that area, actually, and at the time, though, it was just a prediction. It was there was no.
But was there stress affiliated with this time? Was it all fun and games, or did you lose sleep?
For me, it was highly stressful because if you make a prediction like that, you better be right. I mean, and for me, I was sweating it out. I did everything I could to make sure those calculations were right.
And how long would it take you? Like, if you have a really complex calculation you're working on, how long might you spend on one equation?
Well, I mean, I remember there were several dead ends. So one of the central things that we found was that if you compress lithium, it starts in this sort of ordered arrangement where all of the ions are on a periodic lattice and they're close packed. Much like you would find if you, like spheres, stacking spheres, and as you compress it. The number of neighbors of each of the atoms gets the coordination number, as it's called, goes down, and that's our prediction. And eventually, at the highest pressures we looked at, we found that each lithium atom had only one other neighbor, so it was kind of like Li2, And so one of the things that we thought about initially is, why would that happen? Could it be that there's some similarity between H2 and Li2 under high pressure? So Neil made me go through this long tight binding calculation, reproducing Heitler and London's original work on the hydrogen molecule, and only to find that that was not the right explanation. But it was a growing experience, but I remember that I spent like weeks, in stacks of paper going through these calculations. They were all analytic to try to understand, my computation. So it was a lot of, it was very exciting and very, there was definitely stress associated with it, yeah.
And you did, in 2000, you got your PhD from Cornell in physics. How did you end up at the Molecular Foundry?
Well, I was at I did a postdoc at Rutgers, so I worked there with, Karen Rabe and David Vanderbilt and Morrell Cohen and David Langred, and they were, and that kind of was a sort of, I went there mostly because of, it's basically the best place in the world to study oxide materials. From a theoretical point of view, as far as I'm concerned, and because I felt that the work that I had done with Neil, I still needed to know a little bit more about the calculations that I was doing. I think that Neil was basically a very gifted theoretical condensed matter physicist, with intuition that and I had much to learn from him, and his intuition is really unmatched as far as I can tell. But I felt that the electronic structure techniques that I was using for lithium, for studying lithium, that I still needed to know more about them. And so I wanted to go to a group where they had a lot of expertise there. And so I went there. And then after 3 years there, I was kind of looking for different job opportunities, and Steve Louie called me up and told me about this thing called Molecular Foundry. And wondered if I might be interested in coming out and doing that. And at this point, I was kind of looking at a position at Lawrence Livermore National Lab. And coming out here, he was able to persuade me that that the Foundry was, which hadn't been built at that point, was a good opportunity. It didn't take me long to realize that. So yeah.
So as mentioned earlier, your list of current research projects includes single molecule junction charge transport. Can you talk a little bit about what that is, what that's all about?
Right, I think that's something that I have been fortunate enough to have in collaboration with some very good people have some success with in the last few years, and it's something I'm very excited about. Basically, one of the, being here at the Molecular Foundry, I think there are kind of two frontiers in nanoscience, and one is integration. That's why the Foundry is here. People are interested, and it's set up the way it is, with diversity on each floor. The idea is that we'll join together techniques and materials to make some useful nanostructures, that are really integrated materials. And the other, I think, frontier that is sort of almost sounds kind of purpose to that is the ability to address individual nanostructures one by one. So you've got these kind of messy composites that come from the integration part, but then you want to understand how those work. And so there's all of this effort in single molecule spectroscopy in wiring up individual nanostructures. And that's just so, to maybe understand a little bit better, the properties of these novel materials and how they behave in the environments they're in. And so, so one of the things that happened when through the course of the user program was that I got involved with Mark Hybertson, who was then at Columbia, who was a former student of Stephen Louie's. And he introduced me to Latha Venkataraman, who is an experimentalist at Columbia. And at the time, both Latha and Mark were kind of research associates in Columbia's. They had a nanoscience center on molecular transport in nanostructures. And they were both some young people. Well, Mark was a little bit older, but he was effectively young because he'd been at Bell Labs in a different field and was kind of new to the field. And they wanted to do some ambitious projects, and so Latha had worked out a way to measure, to take two macroscopic metal electrodes and contact an individual molecule and reliably and reproducibly measure the resistance of the molecule. So here you're talking about one of the smallest possible nanostructures. This is not even a nanostructure. This is like sub-nanostructure. It's a molecule. And our idea was that they're measuring its resistance, and so maybe so one potential application area that would be molecular electronics. Maybe we could build circuits out of individual molecules. But from my point of view, I wasn't so interested in the application, but just the idea that the audacity of the measurement and the idea that you can control something that small, and measure, not measure a bunch of them in an ensemble, but just one at a time.
So what you're looking at would be how an electron is getting from the wire to the molecule to the other wire.
Right. So here, those are those gold atoms are gold atoms, what's kind of shown in the schematic is way we think a molecule might be lodged in between two gold electrodes.
So this is a theory.
This is a theory. Yeah.
Mm-hmm. And could you replace the molecule with, say, a carbon nanotube or something like that, or would you switch anything out?
So the molecule can get more complicated. One of the things that is sort of, so people have been doing these kinds of experiments for about 15 years, and they're very controversial, And so when I kind of started at the Molecular Foundry, I remember Steve Lewis said, "Well, why don't you start thinking about transport? Let's because from a fundamental theoretical point of view, there's a lot we don't understand about how electrons flow through, small nanostructures. I mean, it's what's called a non-equilibrium process, and so the equations that you have to solve become much more complex. They're already complex, and they just become really even more untractable. And so essentially there's people in the theory community making wild approximations here, there, and some not so wild, but effectively there's no way of normalizing those approximations because there's equal controversy in the experimental community. And so what I think what happened at Columbia was that you have a case where the experimentalists said, look, enough of this. And they basically made a breakthrough where they could reproducibly measure a certain class of molecules that have N groups that are shown in blue here. They're nitrogen atoms that bond with the gold in a very sort of selective and kind of unique way, the same way each time. And that enabled these kind of reproducible measurements. So basically, I think the neat thing about this kind of molecule that the Columbia group discovered was that if you have these nitrogen links here, the mechanism between bonding between the nitrogen and the gold is flexible and unique. And so it turns out that this is another thing that I could basically say, just one last thing would be that, one of the things that I think is interesting about this is that what you'd like to be, so basically from the experimental point of view, they don't have a picture like this. They just have a resistance. They measure the resistance. And what I would like to do as a theorist would be to basically connect the resistance that they measure to the intrinsic properties of the molecule. Okay, then we understand. Okay, but as it turns out that that in this kind of system, I would almost say that's kind of not a well-posed question because when you put the electrode, when you bond the electrode to the molecule, then you're changing the molecule. So it's really what we want. So we kind of, to pose it a little bit better, what we want to do is to connect the intrinsic properties of the junction to the resistance, and so they the group at Columbia really recognized this and designed a link group that made these experiments reproducible. It also they also provided convincing evidence there was a single molecule in the junction. Okay, and that basically for us was sort of, hey, let's now attack this from a theoretical point of view. We can use this really nice data to test our understanding of the theory of transport at the nanoscale, and that's what we did. They basically gave us this great opportunity to test and improve the theory of charge transport at the nanoscale.
And then once you have good theory about this, what do you hope then will happen? What is the next step after that?
Well,
what do you think? Would you like? What would you like to see?
Well, I think that I'm hoping, charge transport is a fundamental process in countless number of devices and applications. One of them is solar energy conversion, and that's something where in a solar cell, light is absorbed, charges are created, and the idea is that you somehow pull these charges out and harvest them in electrodes. You grab the energy from these charges that is sort of, and the energy the charges have are given to them by the photon, that comes from the sun. And so charge transport is a very important, aspect of understanding charge transport. Is a very important mechanism that is going on in solar cells. And in particular, there can be energy loss associated with, as the charge kind of meanders its way out, you can lose energy. So, maybe the sun is yellow, and so you get all these yellow, you get the sort of that sort of is the color of the sun is associated with the frequency of the radiation and its energy. And so the bluer the light, the more energetic it is, and the redder, the less energetic. And so, if the sort of yellow light hits the solar cell, there are all sorts of processes that occur that by the end of the day, because they're not 100% efficient, you cannot get out the same amount of energy that the sun put in. I mean, there's obviously other constraints like the second law of thermodynamics, but still, even so, there are these losses. And so, one would hope that if you could understand the microscopic mechanisms of charge transport at the nanoscale, that maybe we could better understand losses and improve the materials. Now, it should be said, just to be clear, that I'm really not an engineer. So, I mean, I love this application, and it's one of those things that is very important to me. And can I have an impact at a societal level? But I think I also want to have an impact at the fundamental level. And I think one of the important things about the molecular junction work, that, in my view, is that it really does say something new about the way we make approximations to these complex equations that we need to solve to understand charge dynamics. And I think there was something missing, and we had, working with experimentalists that had good data, we were able to find something that was missing and add it to the theory. And I think that to me is equally important, because charge transport may impact solar energy conversion, but there's countless other applications it might impact that I couldn't even dream of, and it would just be, it's very important that we understand, have a firm foundation and understanding of the underlying theory of that in general, I believe. So that's part of the my other interest in the work, I guess.
So I actually heard that they're considering constructing a fashion runway next door on the 3rd floor. Do you know why?
I don't know if... No, go ahead, tell me.
Because you, Jeff Neaton, are a supermodeler.
Oh, man.
Thanks for the groan. So I know we had to quickly go through the science. Or anything else you wanted to say before we open it up? No. One final question. Professionally, what's the thing that gets you up in the morning?
Well, I can tell you that I mean, there's a lot of, I think that, from my point of view, there are the laws of physics, and then there's reality. And, if the laws of physics are very, I don't, I kind of accept those as sort of unchangeable at some level. But they're so, they sort of embody a certain set of equations that are really, though, quite hopelessly complicated to solve in many practical situations. And so, from my point of view, the role of theory is really to try to, do the best one can, make sensible approximations so one can generate new intuition and understanding that will eventually let us, in certain cases, do more than just say, well, we have an equation for that. And so, from my point of view, what I want to do is have impact by, generating new intuition and sort of helping guide experiments and understanding new phenomena that way. I think in terms of what gets me out of bed, I will say this, that I think the lab is a very kind of fun and unique place to work. And the labs, in the sense that, there's a real strong focus on basic science here. But then there's also all these different, it's a national lab, so there's a kind of also this emphasis on society level problems. And so, it's a place where, and I think the lab is done well in the sense that they bring people in to do basic science in an environment where you're bombarded with all of these ideas and concepts that are really important, problems to tackle for the benefit of society. And so I think, in an academic position, sometimes you don't have that visibility. But it is a pleasure for me to get out of bed and come into work here. I think for that reason, because you do get a lot of space to do basic science, but you're almost always inevitably doing it in the context of an important application.
Thank you. So we'll open it up to questions now. So feel free to our audience.
How tall is Bob?
He's tall. Yeah.
It's not just.
But I'm short. I mean, so I can't. I think I'm not sure exactly what. I mean, that's somebody with an iPhone could tell you right now how tall he is. I'm guessing 6'2" or something like that.
Well, here's an audience question from earlier. Jeff from next door, 67, would like to know, ask Jeff how he met his wife. She's a novelist, not exactly standard dating pair for a scientist.
I met my wife at, there was in the physics department at Cornell is right across the street from Goldwyn Smith Hall, which is where the English literature department sits in Cornell. And there's actually a cafe called Cafe Zeus that is, we go to for lunch, and it's where basically physics and English lit meets, and to have soup. And so as a result, I think by the end of my grad school career, I had a lot of friends in that department, and went and